Hi, my name is Duri. I'm an assistant professor at Northwestern University in the Communication Studies Department. And today I am presenting this work on behalf of myself and my co-authors who are at Georgia Tech. This is a project called Xylocode. It is a novel approach to fostering interest in computer science via an embodied music simulation. And this project is really the culmination of a multi-years long effort that has been funded in part by Amazon Future Engineer and in part by the National Science Foundation. The sort of driving question behind this multi-years long effort is how can we design a museum exhibit that uses computational music remixing and tangible interaction to engage middle school age learners in thinking about computing concepts and foster learner interest in computing. So there's a lot going on in this question, so I want to kind of break it down and through that motivate the work a little bit more. So first of all, I want to highlight that the sort of key goal of our research is to foster learner interest in computing. So we're specifically focused on middle school age learners, 10 to 14 years old. We also have some related learning goals, but interest is our primary focus. The next part of the question that I wanted to highlight is the computational music remixing portion of it. So if you've ever listened to a hip hop song, a dubstep song, an electronic song, they all use music remixing. Basically, they chain together music samples, and samples can be looped. They can have effects applied to them. They can be overlaid with other samples, and doing this computationally is called computational music remixing. My colleagues at Georgia Tech have a project called EarSketch, which is pretty widely used in middle and high schools in the United States. And in EarSketch, learners can write Python code, which can computationally remix music and samples. And so it's a way of fostering learner interest in computing through the avenue of music. And this project has been pretty successful in middle and high schools at fostering interest in computing amongst a diverse audience of learners. And we were really interested in how can we leverage the success of this work in a museum exhibit, which is a very different context, very different type of interaction than what you might see in a classroom-based interaction. Finally, I wanted to highlight the portion of this question that focuses on tangible interaction. So we hypothesize that tangible interaction might be an effective way of engaging learners in computational music remixing in museum spaces, based on prior work that shows that tangibles can be approachable and have a low barrier of entry for learners. There's been a variety of projects that have explored how to use tangible programming languages to teach about computing. One of them is Strawbees, which I have an image of here. And there's also been a variety of prior work that has explored how to use tangible interfaces for music making amongst both professional and novice music makers, including this Project React table, which I have pictured here. So we're sort of building on this body of prior work in our project. Briefly, I wanted to talk about two sort of previous iterations of this work. So we've built several different versions of a sort of tangible tabletop exhibit to engage learners in computational remixing in museums. As you can see in these pictures, these two previous versions of the exhibits use sort of block-based programming languages. The first one was a little bit more concrete. The second was a little bit more abstract, but they both used kind of block-based programming languages that were made tangible. There were a number of successful aspects of both of these exhibits, and I refer you to the papers about them to learn more. But I want to highlight, for the sake of our work today, sort of two key challenges that we faced in these previous iterations. The first was they were both built using bespoke hardware, which had a lot of different points of failure, which could, be a problem in a museum where a lot of people are interacting with the exhibit in a pretty rough way over the course of a long period of time. And so we wanted to explore an option that was a little bit more durable. And the syntax in both of these exhibits was also a barrier to entry. So in both exhibits, even though it wasn't a very complex syntax, it was certainly easier than like a full-blown programming language. It still required learners to sort of understand what different symbols meant and how things connected. And when there are only only interacting with the museum exhibit for a short period of time, usually 2 to 3 minutes, that's not a lot of time to learn a new computational syntax. So we were interested in how can we remove this sort of barrier to entry. And one way that we hypothesized we could do this was drawing on previous research on using embodied simulations as a way to foster learning about computing. And these are environments where you can define a few simple rules, and they can create really complex and emergent behavior. So you can define a few rules about how a certain particle moves, or a few rules about how a certain cell is colored, and when you sort of set those into play with a lot of different components, they can create some pretty interesting emergent patterns. And so we were intrigued about how we could operationalize this idea where learners could just set a few simple rules rather than learning a whole programming syntax, but have some resulting pretty interesting musical patterns. So that led us to our research question: how can we design a play space in which learners can engage with computing concepts by modifying simple rules that result in complex and interesting music patterns? We engaged in an iterative design process. I won't go into detail about it here, but I'll refer you to the paper for detail on all of the different iterations of our design. The final iteration was Xylocode, which is a tangible music making installation. It's built using an IDM tangible tabletop, which is basically like a giant touchscreen, but it can also recognize these tangible pucks, which you can place on it, and it can track individual pucks as they move across the table. It's pretty responsive. Very durable. So learners were able to place these sort of frog-shaped pucks on the table. They could tap on the area surrounding the frog to shoot a bubble from the frog, and the bubble would then collide with a line of flowers. And when a bubble and a line of flowers collided, a sound would play. So I'm going to walk through it in a little bit more detail in a minute with some videos, and I think should clarify kind of different aspects of how the system works. Before I dive into that, I just wanted to speak briefly to the tangibles that we used on the table. We 3D printed frogs and custom painted them, and then attached them to the tangibles that came with the table, which have these sort of 3 little feet on them that the table tracks as they move through space. So walking through the different computing concepts that are embedded in Xylocode, the first concept that we embedded in Xylocode was an array. So each one of the lines of flowers that you see on the table is comprised of, is an array, represents an array. And so each flower represents a sound within the array. So when a ball or a bubble collides with the flowers, the current active sound will play, which is indicated by both a color difference as well as an animation. And you can also hear the difference in the pitch of sounds. So the array of sounds is usually along sort of like a scale range. So you can hear the sound differences, and you'll hear that in just a minute. So you can see a video here of someone creating an array of 3 flowers and then shooting a bubble from this frog, and you'll hear a sound when they collide. The next computing concept that we embedded in Xylocode was the concept of a conditional. So you can see here you can create a conditional by tapping this plus button on the area surrounding the tangible. It opens up this little box where you can set a conditional. In this case, this says if the purple bubble hits the red flower, then go to the next flower in the array. So this is essentially prompting the system to iterate through the array if a particular condition is met. And you can add multiple conditionals to one frog, and they sort of collapse into these icons, which you can then expand later, but it sort of preserves the space. There's also this concept of a Boolean, which is sort of embedded in the conditional. So there's this sort of condition that's either always true or always false. So we also have that embedded into the system. So this is someone creating a conditional. Here they are essentially creating the condition that if a purple bubble hits the yellow flowers, so these flowers here, then it's going to iterate through the array, and you will see when they shoot the bubble, you'll see it iterate through the array, and you can also hear the auditory effect. So you can see the animation as it activates the different sounds, and you can hear the sort of change in pitch as it hits the different flowers. Finally, the last computing concept that we embedded in the system is the idea of a global versus local variable. So we had several different global variables: volume, speed, the type of music that the different bubbles generated. So when you change these, it changed and affected all of the balls on the table. As opposed to local variables, there were a couple of these as well. One example is changing the color of the flower array. Just changed the color of like one flower array. It didn't change every flower array on the table. So here you can see some of the global variables in action. You can see they've changed the sound type to violin and now to drums. And then you can adjust the speed of the balls. Finally, I just wanted to briefly highlight that we incorporated tutorial elements throughout the table where you could tap on a little question mark and then view more information, as well as some pseudocode related to a computing concept. And this was also reinforced in signage that we had surrounding the exhibit. This is just a short clip of some of our participants interacting with the table, so you can kind of see what interaction looked like live. Great. So that brings me to our sort of final research questions, which were concerned with sort of evaluating Xylocode in situ on the museum floor. So we were interested in if in a naturalistic setting, does Xylocode increase recognition of computing concepts? I specifically use the term recognition here rather than learning because we were really interested in, can learners recognize this term? If, they come across it later on in a class, could they, recognize it and recall this exhibit and have that interest formation experience? Not necessarily looking for deep or long-term learning gains in this short period of time. Second, we were really interested in whether Xylocode could foster situational interest formation. So are they developing an interest in this topic in the moment? We conducted a study at the Museum of Science and Industry in Chicago where we installed Xylocode on the museum floor. You can see the setup here where we explored these questions. We conducted structured 15-minute interviews with children who appeared to be in the age range of 10 to 14 years old. And the interview, again, was focused on assessing interest development and recognition of computing concepts. And we interviewed a total of 29 different child participants. And our results are described in detail in the paper, but I want to summarize them briefly here. First, we found that the exhibit did appear to foster situational interest development. Learners indicated interest across multiple different constructs that were aiming to assess situational interest development, such as exploration intention, attention demand, and instant enjoyment. We found that the exhibit had an average hold time of 3 minutes and 55 seconds, which is basically the average length of time that a group would interact with it. And while that might sound short, it's actually pretty long for a museum, indicating that learners were developing interest and engaging with the exhibit for a prolonged period of time. Learners demonstrated recognition of certain computing concepts, so they were able to recognize how the exhibit utilized the concept of an array as well as a global variable. But other terms, Boolean, conditional, and local variable, were less salient, or we had more mixed results. So we have several design implications for embodied computer science activities in informal learning spaces that we present in the paper. I won't go through them all here today for the sake of time, but I want to highlight a couple. First, we found that we were able to communicate several computing concepts without needing a sort of block-based programming syntax, which we thought was promising for future work in this area. Second, we found that explicitly designing the exhibit for collaboration with a collaborative workspace in the middle and controls on all sides really encouraged multi-directional, multi-touch interactions and supported collaborative play and practice. We also found that we possibly needed to incorporate more learner-centered design principles in order to scaffold deeper engagement with some of the computing concepts. So, for example, not all of the learners clicked the plus button to add the conditional, so we're interested in how we can encourage that type of interaction in the future. And finally, to end on a fun note, learners really enjoyed and were attracted to the frog tangibles, raising implications for the sort of physical and aesthetic design of tangible interactives. Just to finally summarize, we contribute the design of Xylocode, a novel museum exhibit that fosters interest in computer science through an embodied musical play space. We conducted an in situ evaluation of Xylocode and found that it was effective at fostering interest and recognition of some of the computing concepts, although not all. Finally, we present a set of design implications for embodied computer science learning experiences in museums. Thank you so much. I'd be happy to answer any questions. And I'd also just like to highlight there is a web-based version of Xylocode from an earlier iteration that is still online and available to interact with if you want to check it out for yourself. Thank you.